Hello everyone, welcome to the next lecture. So we are covering chapter number 4 on diodes, and this is lecture number 10. Okay, so in the last lecture we talked about how we can use Zener as a shunt regulator. So today we are gonna start an interesting topic that is more towards applications of the Zener, applications of the diodes. So we're gonna see how we can develop power supplies, and power supplies have different components in it. So we will discuss each component in this lecture, in the next lecture, and we will see how we can develop this constant voltage power supplies. Okay, so by now we have talked about multiple different applications of the diodes. We talked about how we can build logic gates of the diodes earlier in the lecture. We talked about how we can build voltage regulators using Zener diodes. In this lecture, we're going to talk about the signal rectification, which is how we can convert AC signals into DC, and this will play a significant part in building our voltage power supplies. And there are some other applications that we are going to talk about in the next lecture, but definitely that are part of our course before we finish this chapter, which includes limiter and clamping circuits. We will see how we can design certain circuits that will only limit certain voltage values, maximum certain voltage values across the outputs. So we're going to talk about that as well. So let's start with signal rectification, which is the main topic of our lecture today. Okay, so rectifier circuit. Rectification is a process in which we can convert our AC signals to DC signals where they are used. For example, the power supplies that we use to charge our laptops or our mobile phones or other equipment, instruments, devices that we have. And what they do is they go directly into the AC mains, which is an AC source, and they are providing a constant DC voltage to your device to charge the battery. And example could be mobile chargers, right? So we are going to see how that entire, or what's inside that device, what's inside that power charger circuits. So we're going to see that rectification again is an important component of that since the first step is we have 120 volts and 60 hertz signal coming from the mains power supply, and our final goal is to give, for example, a constant 6 volts DC to charge a particular battery, as an example. So we will see how we can achieve that. So the first part, of course, is we want to convert this AC into a DC. Okay, so here is a block diagram of our DC power supply. Now you can see that this DC power supply has different components in it. The first component is a power transformer. This power transformer, so this is our input, right? So this is a plug. This is the main supply that is coming to our homes and everywhere. And this is the final output. Okay, so now what is happening over here is we have this input voltage, which is 120 volts and 60 hertz, and an AC signal that is coming to our homes. We connect a charger to this AC main. So in the first step, we use a transformer inside that power supply, and what this transformer does is it is a step-down transformer. I hope you have already studied the transformers, a step-up and a step-down transformer. Anyways, the function of a step-down transformer is to lower the voltage values, right? So for example, if this is 120 volts, since for example, if I want my output to be 6 volts DC, of course, the first step to do is to rather than having a sine wave of 120 volts, let me make a sine wave of 6 volts. So the first step will be a stepping down. So I will step down my voltage, and I will use a step down power transformer to do it. So let's suppose now I get the 6 volt AC signals after operating that with a step down transformer. Then I'm going to have a rectifier circuit. If you remember some of the basic rectifier circuits that we discussed at the start of the chapter, that it will convert AC into DC. So rather than having this positive waveform and a negative waveform over here, which is an AC, we are going to see different rectifier circuits. What we will do is we will only convert that into a positive waveform. So we're going to have this kind of a DC waveform. Then now this is a time varying time variations, a huge amount of time variations. This is not a constant DC. We are interested in getting this constant DC voltage. On the y-axis we have a voltage. Then we will develop, then we are going to build a filtered circuit that is going to filter out the significant variations in the voltage signal, and we get this kind of a ripple voltage signal, which is much better than this DC, right? This is also DC, this is also DC, this is also DC. But this is much better, right? Because our variations has been reduced, but we can still see some of these ripples in this output over here, which is a time varying ripples. Well, then we are going to use this time varying ripples in the voltage regulator circuit. So we have already designed this as a with a standard voltage, right? If I'm gonna give this time varying component, for example, right? So we saw that 10 volts plus minus 10% variation. If I'm gonna give this to my voltage regulator circuit, I'm gonna get less than 0.5% variation in the output to be exactly constant. So what I will do is I will give this to a voltage regulator as an input, and my output voltage will be a constant DC. So the main parts component of today's lecture is to work on the diode rectifier circuits, and in the next lecture we are going to design the filter circuits. And we have already discussed the voltage regulator. So these are all the main components of the power supply that we need. All right, so let's start with, very quickly I'm going to talk about this first component as well, power transformer, and how to design it. And then we're going to move to the diode circuits. All right. I kind of discussed all of that. So the first component is a power transformer, again a step down transformer, which is a type of a transformer which has a high voltage at the primary side, right, 120 volts, and it will convert that to a low voltage at the secondary side, which is a voltage that we kind of required. Similarly, in terms of the windings now, I don't know if you already know how to design the transformer step down or step up transformers. Essentially what you do is very simple. There's a bunch of other components, but the most important component and the main component is to change the number of the windings, coil windings on the primary or the secondary side. So what we do is, if we want to have a step down transformer, the windings on the primary side are going to have more turns as compared to the secondary winding. And how we can determine this using this formula. This is our input voltage, which is 120 volts. This is our output voltage, for example 6 volts, and then we can design this ratio N2 over N1 such that we get our output can be equals to Vs. N1 is the number of windings on the primary side, N2 is the number of windings on the secondary side. So we can see that if our N1 is higher than N2, we can design a step down transformer in which our output on the secondary winding is going to be lower compared to the primary winding, right? So N1 is on the primary side, N2 is on the secondary side. Another important consideration here is transformer. Also this important transformer that is present in all of these power supplies that provide a constant DC voltage. It also has another important purpose, and that is it provides an electrical isolation in between the power line circuit, the main power that is coming in, and our electronic equipment. For example, if there is any power surges or anything else, the first thing that will get damaged will be the transformer, and our electronic equipment can be saved. Right, so this also minimizes the risk of electric shock to the equipment user. So this is, again, step down transformer plays a very important role. Okay, so this is a step down transformer. Now let's talk about other components. We kind of already discussed that, so I'm going to briefly talk about that as well. Diode rectifier circuit, as I mentioned earlier, rather than having a step down voltage like this, what we do is we want to convert that into a DC voltage like this. So this is what our rectifier circuits will do. They will convert a bipolar output waveform to a unipolar output waveform, right? And we know that although this is still DC voltage, but there is a significant variations considering in the voltage, significant variation in the voltage considering time, right? So we still, this is not desirable in terms of charging our batteries. We need a constant voltage. So that is why we, the next step that we do is we use a filter. So that filter will help reduce some of these variations, right? So the filter will help reduce the variations, and it is going to behave something like this. There is going to be still some minor variations left in the voltage signal that are time dependent. So after the filter, the next thing is a voltage regulator. It could be a regular Zener voltage regulator, where we convert this into our exact constant with a very minimal variations in the output voltage. So this is what we want as a voltage regulator, that we want it to regulate the voltage irrespective of this variations and irrespective of the variations in the load current. So that is why, and we already kind of discussed how to design the voltage regulator using forward conducting diodes and using Zener diodes, which we operate in the breakdown regions. For the power supplies, mostly we use Zener shunt regulator configuration that we discussed in detail in our last lecture. So we are not going to discuss that again. In the power supply, we are going to mainly cover rectifier circuits and filter circuit. And finally, load is that electronic equipment that requires the DC output for charging. It could be your smartphone, it could be your laptop, or anything else. Okay, so these are all the components. So we are going to, let's start with the diode rectifier in today's lecture. In the next lecture, we're going to start with the filter. All right, we already started talking about this half-wave rectifier circuits much earlier in this chapter when we introduce a concept of what a diode is, and we saw that how it can rectify the signals. So this is what we have already seen before, right? This is your input voltage that is connected to a diode. This is your diode, and we are going to assume this to be an ideal diode model. An ideal diode model is, if you remember, that whenever your voltage will become greater or equal to 0, this will become short circuit, and whenever voltage is less than 0, this will become open circuit, right? So and the potential drop across, right, in a short circuit case, potential drop across will become equals to 0 volts. Short circuit, 0 volts, potential drop, right? Okay. So assume now this is our input voltage. So in this part of a cycle, we can see that as the input voltage is negative, as this input voltage is negative, this anode will be negative with respect to the cathode, and our diode will be reverse biased. This means that it will be an open circuit. So when it will be an open circuit, the output voltage will becomes equals to 0, right? So this is VD. Output voltage will becomes equals to VI. In this case, the output voltage will becomes equal to 0 volts. Okay, so in this case, we can see that our output voltage in this entire, when it is reverse bias, it will continue to be 0 volts. Now in this forward conducting cycle, as this cycle is going to come in, let's start it with the blue. In this entire cycle, when your voltage is greater than 0 volts, your diode will become forward bias. This means it will become a short circuit. So this entire thing will appear as is across output because of this V naught equals Vi. Now as it go back again in the negative direction, the diode will again become reverse bias. We get this condition, and it will again be cut off. So this is how we do the rectification, and this is what we have discussed earlier as well as an example in the earlier part of this chapter, right, in which we are using this simple diode circuit, a simple single diode, and we are doing this rectification. We are converting this AC signal to DC. And another thing that we can see over here, this is something that is called as half wave rectification. We are only getting the rectification done in this positive cycle, and in the negative cycle, we don't get any output voltage. So that is why it is called as a half wave. Shortly, we are going to develop another circuit model where we will be able to develop a full wave rectifier circuit, which is going to rectify both the positive and the negative waveforms into the DC signal. Okay, so this is what we have discussed before. Now I'm going to show you how the circuit will behave when there will be a constant voltage drop model. Okay, so constant voltage drop model is a more realistic model in which we kind of determine that VD is approximately equals to 0.7 volts, something like in IV characteristics, right? It was something like this, right? So we saw that, and this was a VD. So as long as this voltage is less than VD, when this voltage across the diode will be less than the threshold voltage, or in this case it will be less than the voltage or the barrier voltage, nothing will flow, no voltage, nothing will flow, and it will behave as an open circuit, right? So during this entire condition, when the input voltage, which is Vs here, is less than the Vd value, nothing will, our output voltage will be 0. And as soon as this voltage becomes equal or greater than Vd, as soon as this will happen, it is going to behave as a short circuit. Okay, so it is going to behave as a short circuit. So in this case, it will be an open circuit, and in this case, it will be a short circuit. Okay. So as soon as our input voltage will become equal or greater than the VD, it will become it's essentially will not become a short circuit. There will be a potential drop of VD will appear across the diode, right? So in this case, we're gonna have a VD appearing across this. So this VD, so the output voltage will become equals to Vs minus VD when VD is greater or equal to, when Vs is greater or equal to VD, right? So, all right. So, looking at this characteristic again, simply in a constant voltage drop model, as our input voltage, this Vs, is less than the VD, we can see that it is in the reverse bias condition, nothing is flowing, it will remain as an open circuit, right? And our output will be equals to 0. So this is reverse bias condition, and this is forward bias condition. What will happen in the forward bias condition is, in a forward bias condition, we will that will appear when our voltage will become equal to or greater than the value, this VD value, which is normally 0.7 volts for silicon-based PN junctions. Okay, and this means that a 0.7 volts will appear over here across the diode in that case, and the output voltage will become Vs minus Vd. Right, so before Vd, diode will not conduct because of the depletion region, and the output voltage will be 0. And as soon as the Vs approaches Vd, diode will start to conduct, and there will be a 0.7 volt appearing across it. In terms of the transfer characteristics, we can see that where our x-axis is our input voltage and our output voltage is on the y-axis, we can see that as long as our Vs is less than Vd, our output voltage is 0, right? And as soon as the Vs becomes greater or equal to Vd, our output voltage becomes over here, right? Slope is approximately equals to 1, Vs minus Vd. So this is how we can draw this transfer characteristics in between input and the output voltage of this rectifier circuit. Now let's look at the voltage waveforms as well of this rectifier circuit. Okay, so this is how it looks like. This is a time varying component, this is the output voltage. So actually this shows both the input and the output voltages, where black line over here shows the input waveform, and the blue line over here shows the output waveform in this figure. Okay, now this is a constant voltage drop model, which means, let me write the conditions again. As long as the Vs is less than Vd, output is 0. And as soon as Vs becomes greater or equal to Vd, output becomes equals to Vs minus Vd. Okay, so these are the conditions of this constant voltage drop model. Now, okay, so let's start to look at this waveforms. Okay, right. Okay, so this is in this case, everything is 0. So diode will be reverse biased. The output will be 0 as well. Now what will happen is during this phase, right? So this is the input and this blue is output. What will happen during this phase is, during this phase, we can see that our voltage is increasing, and at this point, it will become equal to VD. So in this entire region, the voltage, input voltage is still less than VD, right? So when the input voltage is less than VD, output will remain 0. So that is why our output is still 0 over here. And now as soon as this will increase from VD, our output will also start to increase. So the maximum output voltage that we can get is what we are gonna have. So we are gonna have the maximum output voltage that we're gonna get is this Vs minus Vd. So that is why this will never reach a peak. So when this will reach a peak, there is going to be a difference of Vd, potential drop of Vd over here. So this potential drop is also equals to Vd. And similarly, as soon as our input voltage will fall below again Vd, we will go down into the cutoff mode, and our output voltage will become equals to 0. So in a constant voltage drop model, we will realize that our rectification is not like, so earlier we saw that our rectification is something like, so this is, our rectification was happening exactly overlapping with it and then 0. However, we saw that in a constant voltage drop model, this will not happen, because in this region, it is still 0 because of the constant voltage drop, and then it will again become 0 as soon as it will fall less than Vd. So that is a much more realistic case, because we have a constant voltage drop model very closely relates to the exponential model, which is a real model of a diode. Okay, so this is what we discussed. As the input voltage reach Vd, the diode will start to conduct and V0 will start to appear. Maximum V0 will be Vs minus Vd. We talked about this. And as soon as the output will go below Vd, so this point, diode will again stop to conduct and the output voltage will become 0. Alright, so this is again, and so this is another example where we have used a constant voltage drop model, much more balanced model than an ideal diode model. But still, this example is also an example of a half-wave rectifier circuit, right? So we are going to do another example in this lecture where we are going to develop a full-wave rectifier. All right. So before we go there to develop a full-wave rectifier, I want to talk about. So while we develop these rectifier circuits, we need to consider some of the important design considerations or limitations, and the most important probably is what is the right diode to select in terms of what are the specifications that are needed. So one important specification that is needed is the current handling capacity of the diode. We can determine this by finding out what is the maximum expected current diode or the circuit is supposed to handle, right? So what we will do is we are going to analyze our circuit, or we are going to come up with some expectation. Okay, so this is the amount of the current that we expected to flow through the diode, so diode should be able to handle that current. So its current handling capacity is important. The second important specification that is needed is something that is called as peak inverse voltage. Peak inverse voltage is whenever we are operating the diode with the AC signals, right? It will become forward bias, reverse bias. So there will be a reverse voltage, a maximum reverse voltage that can appear across the diode before it will permanently damaged. So we need to determine that voltage. We need to select a diode such that whatever the maximum reverse voltage that will appear across the diode, our diode should be able to handle that reverse voltage without breakdown. And that is important. We don't want diode to go into the breakdown. All right, so how we can determine this voltage? So what we do is in our circuits, and we're going to do examples in the examples as well. how to determine the PIV value. So, but the PIV is, as the name suggests, it's a peak inverse voltage. So it is a maximum inverse voltage that we expect to appear across the diode. So we will see how we can do that, right? For example, if I will go over here, what is the maximum voltage that we think will appear across the diode? Inverse voltage. So we saw that the maximum voltage, maximum reverse voltage that can appear across the diode. So that will happen when the diode will be reverse biased, right? This is a constant voltage drop model, right? Okay. So we have a VS signal, and we are assuming the VS signal to be, so this is our VS, right? So this is our VS signal, and it's a sinusoid. And we saw that the diode will become reverse biased as long as when the voltage will start to go down less than 0 volts. So what is a maximum negative voltage that will appear across the diode will be this. So the maximum reverse voltage that is going to appear will be equals to the maximum negative of the waveform in this case. So it will be equals to Vs. Right, so this will be the minus Vs, that is the maximum that is going to appear across it in terms of our reverse voltage. When we say it's a reverse voltage, so it will be so the maximum voltage, reverse voltage that will appear across it will be equals to Vs. Let me go back. Okay. All right, so this is the maximum voltage that will appear across it. Now another important thing in terms of selecting the diode and it's selecting its PIV value is that we want to make sure that we will select a PIV such that the reverse breakdown voltage or the reverse breakdown voltage of that specific diode is at least another 50% greater of that value, right? So whatever the value that we get over here, we should take another 50%, add another 50% of that voltage value, right? So it should be Vs plus 0.5 Vs, 1.5 Vs, or whatever the PIV value that we get, right? We should select another greater than 50% of that value to make sure that it will never enter into the breakdown region, even if there is a variation in the peak inverse voltage that can appear across the diode. Even if more voltage will appear across the diode, slightly more, so it shouldn't even enter into the breakdown region. So we want to select our PIV value considering that parameter. Okay, now I am going to switch gears, and now we are going to develop a full wave rectifier circuit. Full wave rectifier is, our input is this, and our output ideally should be something like this, right? Something. So this is a full wave rectifier in which I am converting. Oh, sorry. This is, yeah. Our output should be this, something like this, right? So this is a full wave rectifier circuit. So let's develop one. How we can develop that? Okay, so full wave rectifier circuit rectifies both halves of the input sinusoid. So it is going to rectify both the positive and the negative waveform. Here is one example of that. In this example, we are again going to use a constant voltage drop model. What do we have here is we have a transformer that is stepping down the voltage from the AC 120 and 60 to whatever the voltage is that we need for the power supply from the constant DC for the equipment. And we connect these two diodes in this way. And this transformer is a special type of transformer which is called as a center tap transformer. In this center tap transformer, what we will do is we kind of take another connection from almost at the middle of the windings, such that we can divide the secondary winding into two halves, and we have the similar voltage appear across both of the halves of the secondary winding. So this transformer is called as a center tap transformer. So now our secondary winding is center tapped. This means that we have two voltages appearing over here, right? And we connect these diodes D1 and D2 in this configuration at both of these lines. Note down all the connection. This center tap line is going directly to the ground, and then this diode D2 is directly connected to the load resistance over here, right? So we are gonna have this V0 appearing over here. Okay. Now let's look at what will happen in the positive and the negative cycle. Okay, so what will happen? What will happen in the positive cycle of the input waveform? Okay, so let's see. This is your This is your waveform. So let's see what will happen in the positive cycle. When you're gonna have a positive cycle, right? So in a positive cycle, what will happen is that diode will become forward biased. Of course, once it will cross a barrier voltage, VD. But in a positive cycle, the D1 will start to conduct. Let's call this as VI or VS. What they're using? VS? Okay, let me use VS. Right, so this is your input voltage VS. Right, so what will happen is you have when during the positive cycle of this waveform, the diode D1 will start to conduct because it will become forward bias as soon as this VS becomes greater than VD, right? Because it's a constant voltage drop model. Anyways, this will become forward bias, and this VS over here will become reverse bias. And why that will become reverse bias? We have a positive cycle that is coming over here, positive cycle that is coming over here. So we have a negative voltage that is appearing here. Since we have a negative voltage that is appearing here, so this means that D1 will be off, D1 will be on, and D2 will be off. So what we will get is this is directly connected to the load resistance and our V0. So this means that my positive cycle will get rectified, or my positive cycle will appear in the output. So in my output, I'm going to get my positive cycle. Again, with the loss of VD, so it will be VS minus VD. Okay, so again, okay, so let me talk about the negative cycle as well. And what will happen during the negative cycle? When my negative cycle is going to come in, we can see that this negative voltages is going to reverse bias this D1 and forward bias this D2. And when this D2 will be forward biased, so we can again see that this is directly connected to the load resistance. So again, our output voltage will be rectified. So we're gonna get a positive rectification of both the positive and the negative cycles. So let's look at the positive cycle of the input waveform again and the negative cycle. Right, so when our AC input line is at the positive over here, right, VS at the secondary will be positive. So for example, again, in this positive cycle, this is positive, this is positive, this is also positive. But this positive makes the D1 forward bias. This positive will make the D2 reverse bias because D2 is connected to the negative terminal of this winding. Okay, so D1 will conduct and D2 will be reverse bias. Current will flow through R and back to the center tap, right? So current is going to flow through this resistance and back to the center tap to complete the circuit, and we're going to get the rectification. Similarly, during the negative cycle, both VS will become negative, right? So both of these VS will become negative, these VS. So this means that when this VS will become negative, this is going to reverse bias D1, and this is going to forward bias D2. And now this again will go over here, and back to the center tap to complete the circuit. So we're gonna get rectification in both the cases. Right, so now our D1 will be reverse bias and D2 will conduct. And right, and the circuit flow is that it's gonna flow through the resistor and back to the center tap, which we talked about. Important thing is why we get a rectification at the same positive rectification, because the direction of the current flow is the same, right? So let me again quickly show. Right, okay, so when the positive cycle will come, this will conduct, right? And this is our flow of the current. When the negative cycle will come, right, so this will be off, this will conduct, and this will conduct again. This is gonna go over here, here, and here. So we can see that the direction of the current is in the same direction, and that is why we will get our, for both of these cycles, for both the positive and the negative cycle, for both the positive cycle and the negative cycle, we get this rectified output. And since this is a constant voltage drop model, so we saw that our rectification is only done, right? Our rectification will start to happen when Vs will become greater or equal to Vd, and when Vs will be less than Vd, it will be reverse biased, and it will be forward biased, any diode. So this is a constant voltage drop model. Okay, so let's look at the transfer characteristics for a full wave rectifier. So this is the transfer characteristic again. This is the input and this is the output, and this we can easily determine that, right? So as soon as our voltage, and this is when the D1 is on, D2 is off, this is when D1 is off and D2 is on. So as soon as our input voltage becomes greater or equal to Vd, the diode 1 will start to conduct, and this is the voltage drop that will start to appear across the output. And similarly, when our negative cycle will start to drop less than Vd, our diode 2 will become forward biased and will start to conduct. And this is a potential drop that will appear across the resistor. Again, this potential drop is usually in the same direction. The current flow is in the same direction. That is why we get the rectifications in the same direction. Right, so this is what we discussed already. For a positive half cycle, as Vs approaches Vd, D1 will conduct, D2 will be off. For negative half cycle, as Vs approaches minus Vd, D2 will conduct and D1 will be off. And so, right, so we already know that we discussed earlier that the full wave rectifiers are better rectifiers than half wave rectifiers because it is rectifying both the cycles of our input waveform. Okay, so let's do another example over here, and let's see what is the peak inverse voltage that is appearing across a full wave rectifier. Okay, so let's see this example. Assume that the D1 is conducting and D2 is reverse biased. So what we are interested in finding, what is the maximum peak inverse voltage? What is the peak inverse voltage that will appear across any diode? So we want to select a diode with a specific values, right? So that they won't enter into the breakdown region. So let's determine what is the peak inverse voltage of these diodes. In order to determine that, we want to see what's the maximum inverse voltage that is going to appear across it when it is reverse bias. So we can pick any cycle, positive or the negative one. So let's pick a positive cycle. In a positive cycle, we can see that, right? So we kind of saw over here, in a positive cycle, the diode 1 is conducting and diode 2 is off. For a positive cycle, when a diode 1 is conducting and diode 2 is off, meaning that diode 2 is reverse biased. So let's find out what is the maximum reverse bias voltage that will appear across it during the positive cycle, and that will determine the PIV. Okay, so in the positive cycle, so right, and D2 is off, so what is the voltage that is appearing? So in the positive cycle, D1 is conducting, so the voltage that is appearing over here is V0. So at this terminal, we have a V0 appearing at D2, and at this terminal, what is the voltage that is appearing? We have a Vs, so this is a negative Vs, so we have a negative Vs appearing over here. So the total reverse voltage will be equals to, right, will be equals to V0 minus Vs, so it will be V0 plus Vs. So this is a total reverse voltage that is appearing across a diode, D2. Okay, so the total reverse voltage, when the diode D2 is reverse biased, at its cathode, the voltage appearing is V0 as we discussed, and at anode it is minus Vs because it is reverse biased and a positive cycle. So the total voltage, that is reverse voltage, that will appear across the diode is V0 plus Vs. Okay. And this voltage, when this voltage will reach at its maximum value, since we are interested in finding what is the maximum reverse that can appear over here, so we need to look into slightly more detail. So this is a voltage that is appearing, reverse voltage that is appearing across the diode. And do we have any, and we can see that this value is changing, the value of the V0 is changing, And the maximum value of the V naught will happen when, what is the maximum value of the V naught? The maximum value of the V naught is Vs minus Vd, right? You can also see it over here. This is the maximum value of the V naught. So this is the maximum value that will appear across the Vd. So in order to find the maximum peak inverse voltage, we can replace this V naught over here, right? So we have V naught plus Vs equals, V naught is Vs minus Vd plus Vs, so it will be 2 Vs minus Vd. So this is the maximum inverse voltage that can appear across the diode. And this will be our peak inverse voltage. So this is how we can determine a peak inverse voltage of a full wave rectifier circuit. Okay, so this is the end of this lecture. In this lecture, we started with the power supply concept. What is inside the power supply? We saw that there is a step-down transformer. There is a rectifier circuit. We need rectifier. We studied a half-wave rectifier circuit and a full-wave rectifier circuit. We talked about a center tap using a center tap transformer. We developed this full-wave rectifier. There is one more full-wave rectifier that we need to design, and we will do that in the next lecture, which is called as a bridge rectifier circuit, bridge full-wave rectifier circuit. So we are gonna study that in the next lecture, and then we will, in the next lecture, we are also gonna start talking about how we can design the filters to minimize these as a next step of the transformer, as a next step of the power supply, where we want to minimize the variations of our output voltage. Okay, so I will talk with you in the next lecture, and with that, thank you so much. Bye bye.